Okay. Yeah, thank you. So, yeah, I'd like to thank the organizers and all the staffs at the Galileo Galilei Institute for, making this happen. So, yeah, I'm Masaki Oshikawa, and as yeah, he told you, I recently just moved from University of Tokyo to Ohio State in US, and so I'm wearing this Ohio State T-shirt. Um, so I was asked to give some review talk. So I decided to talk about some very old subject or standard subject. So maybe everyone already knows, um, but that is conformal boundary conditions of free bosons and their Z2 in 1 plus 1D. My entire my talk is about 1 plus 1D today. Um, but those are very old stories, mostly based on those very old papers. But sometimes old stories have new applications. So in the second part, I'm going to discuss some new applications of this stuff, especially about so-called quantum magic in 1D quantum many-body system. So in this paper, we discussed something different, entanglement swapping or measurement-induced entanglement in many-body system, but probably I don't have time to discuss this part. I hope I can discuss this uh, first one. Okay, so let me start from very simple thing, free boson. So I consider free boson field theory in 1 plus 1 dimension, and this may be defined in terms of Lagrangian density. Then, of course, this is free theory, so basically you can solve everything. But surprisingly, this free boson field theory is very rich. And one indication is that often in physical applications, this field phi is something like an angular variable. So in high energy jargon, this phi is like a compactified. That means that so if you increase phi, eventually you come back to the original physical state. So we impose so-called compactification. So we identify phi with phi plus 2 pi r. So in this language, this r is like the radius of this circle, and this phi takes a value on this circle. And actually, if you change r, then Lagrangian density is the same, but actually critical exponent and so on changes continuously as a function of this r. So this r is very important parameter. And if, I don't know, most of you guys are from field theory or high energy maybe, but in condensed matter context, this R corresponds to so-called Luttinger parameter, if you are more familiar with this terminology. Anyway, so then I don't, probably everyone knows, but if you have this field phi, then you can always introduce so-called dual field. Then the same theory can be described in terms of the dual field with the same Lagrangian. Um, but this field is again compactified. But the compactification of theta is related to compactification of phi, but in an opposite manner. That is, theta is now identified with 2 pi over r. So compactification radius r changes to 1 over r in the world of theta. And this duality between phi and theta, I think in high energy world, this is called T duality. Then, yeah, I want to talk about the conformal boundary conditions. Then, the natural candidate, of course, is that so you have a bulk with where this boson field is defined, and you have a boundary, and you want to realize some boundary condition which is conformally invariant. But even if you don't know any conformal field theory, you can think of a natural boundary condition that is, so let's say this is x, and so this boundary is at x equals 0. Then one natural boundary condition for this free boson is at the boundary, this takes some constant, let's say 0. So this is nothing but Dirichlet boundary condition. And also another natural boundary condition is derivative of this field at x equals 0 is 0, let's say. So this is Neumann boundary condition. And these are very natural boundary conditions for free bosons. And it turns out that you can verify that these boundary conditions are indeed conformally invariant and satisfies all the consistency requirements. So this actually turns out to be really legitimate conformal boundary conditions. And then interesting thing is that, so I mentioned that there is always, you can always define dual field. And in terms of dual field, you can describe the same boundary conditions using the dual field. Then this Dirichlet boundary condition for phi is equivalent to Neumann boundary condition for on theta. And this Neumann boundary condition on phi is equivalent to Dirichlet theta. So in terms, there is also duality in terms of the boundary conditions. Yes. Yeah, I will come to that. Yeah, yeah, thanks. Yeah. Um, yeah, so for that, you can explicitly write down the so-called boundary state for Dirichlet and Neumann because so in this picture, this is space, and boundary is just imposed at one side of the space. That's maybe standard way, maybe the most naive way of describing the boundary condition. But you can rotate this picture in space-time. Then now you can interpret this direction as time. Then this boundary can be replaced by some initial state, which is called boundary state. And you can write down boundary state explicitly for Dirichlet and Neumann. And in terms of phi and theta, and you can see, yeah, yeah, you can, yeah. So this is not trivial. Yeah, you need to do calculation, but I'm kind of skipping the details. Yeah. Mhm. Yeah. So yeah, indeed. Yeah, thank you. Because of the compactification, so this is more like a phi equals 0 modulo 2 pi r. Yeah, and likewise. So in terms of theta, yeah, also equals to 0 modulo 2 pi over r. Yeah. Mm-hmm. Uh, Sorry, by invariant you mean oh, okay. Yeah, so okay, so of course this is not how to say not totally rigorous because of the compactification. So when phi is compactified, this is not in some sense well-defined quantity because of this. So in order to make a well-defined quantity, you put this phi in exponential. So exponential of I phi over r. That's uh, uniquely defined under compactification. So you can always discuss exponential of phi applied to the boundary state. Then it returns a unique value as an eigenvalue. That's probably more rigorous formulation. So this is just a kind of slogan. No, okay, that's very good question. So I'm just saying that these are legitimate conformal boundary conditions. Then even for the single component bosons, there are so-called exceptional boundary states, boundary conformal invariant boundary conditions, which involves more um, complicated construction. But yeah, I'm not saying these are the only ones, but those are most natural and indeed conformal. But there are other boundary conditions. Yeah. Um, yeah, good question. But actually, hmm, yeah, I'm coming to related question later, but in fact, the conformal boundary condition of conformally invariant boundary state has to satisfy many consistency conditions. So it's not very, how to say, uh, there is not much room to. So I think if you try to make a linear combination of these two conditions, then I guess that doesn't work. So I'm not totally sure. Yes. Yeah. Yeah, so right, yeah. And another way of saying is that you, so in the bulk you can decompose this phi to right mover and left mover, and phi is sum of phi right mover plus phi left mover. Then the dual field theta is the difference, phi right minus phi left. So if you take linear combination, basically you are imposing some condition like only right mover vanishes or something like that. But I think that cannot be imposed consistently. Yeah. But at least these two are legitimate conformal invariant boundary conditions. Then, so this is a special case of more general conformal invariant boundary condition of conformal field theory. And when you have conformal invariant boundary, then in general, if you have conformal invariant boundary condition, then let's say this length is L. Then, so compared to bulk, because of the presence of boundary, in general, you have extra boundary energy. So that's, and the boundary energy is basically proportional to the length of the boundary. And for example, if you consider Ising model or something, then when you have a boundary, there's generally boundary energy. Of course, in some special case, you can tune this to zero, but generically this exists. But the point is that this is non-universal quantity, meaning that this boundary energy per length depends on all the details of the lattice model and so on. So you cannot predict this boundary energy density from field theory. This is, in high energy terminology, this cutoff dependent. This is non-universal. But there is another physical quantity you can use to characterize this boundary is boundary entropy. Which is often written as log of g. And if g is integer, this can be interpreted as a ground state degeneracy. But in general, this can be some fractional or even irrational number. And interesting point is that this boundary energy is universal, meaning that even for lattice model realization, you can predict this number by field theory. So this is universal. And this presence of this universal boundary entropy was first pointed out by Affleck and Ludwig. So this is often called as Affleck-Ludwig boundary entropy. Yeah. Well, so this by universal, I mean this is completely determined by CFT, and Yeah, yeah, of course, yeah, yeah, yeah. Of course, it depends on boundary condition, but once you choose bulk CFT and then choose confound invariant boundary condition, then um, this number is universal in the sense that it doesn't depend on microscopic details, how you realize. Yeah. And in principle, at least, you can compute this by numerics, but it doesn't depend on microscopic detail. Okay, so this is general statement, and these are special cases. So also for these simple boundary conditions, these Affleck-Ludwig boundary entropies are well defined, and you can calculate explicitly, but I skip how to calculate this, but it's kind of known. So, so Affleck-Ludwig boundary entropy is log G, and for Dirichlet boundary condition, this number G is given by 1 over 2 to the power of 1/4 and times 1 over square root R, and R is compactification radius. So here you can also see that this universal quantity depends on the compactification radius. And once you know the Dirichlet boundary condition, the result for Dirichlet boundary condition, you can immediately obtain the boundary entropy for Neumann boundary condition, because this Dirichlet is dual to Neumann. So if you switch phi from theta, then you can switch from Dirichlet to Neumann. And this duality between phi and theta is given by flipping this radius from R to 1 over R. So, so it's given by the same coefficient, but you flip R to 1 over R. So you should get this number. And this is related by T duality. And so far so good. Then now I want to consider, let's say, n copies of the same free boson field theory. So to compute this, you compute a partition function, and so you, for example, for example, you impose a periodic boundary condition on this side and impose boundary condition on left and right as Dirichlet boundary condition. Then this determines Dirichlet to Dirichlet amplitude or partition function. And then, so Cardi says that if you look this direction as a time, then this partition function can be identified as with a spectrum of operators, because you have finite widths, and so the time evolution is like time evolution is generated by Hamiltonian. So the spectrum of Hamiltonian is related to the finite size spectrum with Dirichlet boundary condition. And so each operator appears in this spectrum. So you can expand this partition function as some exponential of minus ground state energy times some factor plus 1 plus excited energy. And if you regard this vertical direction as a time or imaginary time, then each term in the expansion can be identified with energy level. So these should appear with multiplicity 1, or so you must have integer coefficient. That fixes the normalization of the partition function. But then you can rotate this picture to switch space and time. And now this is a direction of time evolution. So this is where this boundary state formalism comes in. So in this picture, the same partition function can be regarded as some amplitude from this initial state to final state. And then you should be able to express the same partition function using this boundary state. Then this normalization of the boundary state gives this G. Yeah. Yeah. So this is exact. Yeah. So yeah, this yeah, you can fix coefficient of this partition function from physical requirement given by Cardi. Then that fixes the coefficient normalization of this boundary state, and that fixes this. Yeah, so this is exact. So now I consider n copies of the same free boson field theory. And in many condensed matter and also quantum information, which I hope to discuss in the second part, this situation appears frequently, especially if you try to compute some, entanglement entropy or some kind of entropy, then the useful trick is to use replica trick. Then you need to introduce replicas of the same CFT, but they are somehow coupled at the boundary. So let's say you don't do anything on this field theory in the bulk, but only introduce a coupling in the boundary. And let's say I introduce interaction like a cosine of phi 1 minus phi 2 and cosine phi 2 minus phi 3. This kind of interaction. And actually, it depends on the compactation radius r, but sometimes this interaction is relevant. So even if you add small interaction in the low energy limit, eventually this dominates. Or you can just imagine sending this lambda to infinity. Either way, I suppose that you have this interaction and somehow lambda goes to infinity. Then at the boundary, this interaction pins phi 1 to phi 2, and the phi 2 is pinned to phi 3, and so on. So this interaction forces boundary condition phi 1 equal phi 2 equal. So all 5 fields should take the same value at the boundary. Okay, so yeah, later I will, discuss example why, but here I'm just assuming that I have this kind of interaction. Yeah. And let's say this is relevant, RG relevant, then in the low energy limit, this grows to infinity. Then I want to ask, okay, so suppose this boundary condition is enforced, and then what is the Affleck-Ludwig entropy of the resulting boundary? And as I said, this kind of situation often appears in condensed matter, and the common trick people often use is to change the basis. That is, you can introduce a center of mass field. Phi 0, which is sum of all the components, maybe probably normalized. And then other new basis differences. Yeah, there are, the choice is not unique, but you can define new bases using only differences. And then you have up to phi of n minus 1. Yes. Just just actually, I'm going to say that this is not quite correct, but this is one naive way, that's, to keep the length or something. Yeah. So if you use this basis, then these difference fields are pinned to 0 by this interaction. But there is no restriction on this center of mass. So it looks like this behaves like Neumann, Dirichlet on these difference fields. And this center of mass field at the boundary behaves like under Neumann boundary condition. Center of mass is not, because this isn't fixed, so it's fluctuating freely. Okay, so maybe I should say that in the beginning, before putting interaction, they were all subject to Neumann. And then I introduced this lambda interaction, which only pins the difference. Yeah, thank you. Yeah. So if you use this trick, then it seems like you can compute this Affleck-Ludwig entropy. That is, G should be one component obeying Neumann, and other component obeying Dirichlet, and there are n minus one component obeying yes. Um, well, so I mean, so initially every component is subject to Neumann, and then you just introduce this cosine potential only for difference field. So I think, yeah, this kind of natural expectation. So if I use this, then this is and I think, yeah, you would get something like this by just multiplication. And yeah, this looks like a reasonable because, so the Lagrangian was completely free. So you can change the basis of the field, and still Lagrangian is free boson. And these fields look like independent. Then this should follow. But actually, it turns out that this is not correct. And I'm going to explain why this is wrong. And this is actually related to a question by Frank. So let's consider a particular case of two layers. So there are only two layers, phi 1 and phi 2. Still, you can define this center mass field and the difference field. And the difference field is pinned. But then this interaction imposes phi 1 equals phi 2. So this is a situation for n equals to 2 case. But actually, this is equivalent to you have just a single field, and you don't have any boundary or defect or anything. And so if you like, there is an identity defect. There is nothing. But you can artificially choose this point and for the system. Then if you fold this system, you can map the system to this one. So this is identity defect. Which means nothing, just a bulk. But if you fold this system, then you can reproduce this. So for n equals to 2, this answer gives, so this factor cancels n equals to 2, then 2 minus 3 is 0. But you still have this factor. So this theory predicts g equals to 1 over square root 2. But since this situation is equivalent to identity defect or just nothing, just a bulk, and you artificially folded the system. So there shouldn't be any boundary energy or boundary entropy for this identity effect. So at least for n equals to 2 case, you should have g equals 1. That's a zero entropy, zero Affleck-Ludwig entropy. So for n equals to 2, this should be the correct result. But if you apply this argument, you get this. So this is wrong. I don't know. Maybe you can interpret this that way, but well, I'm just dealing with a compact file, free boson, so. Mm-hmm. Yeah, if you properly normalize, it's still the same. But actually, there is some subtlety about going to this basis. That's a point. Yeah. So. Mhm. Um, but in some sense, this is still correct because in the bulk, phi field was just freely fluctuating. So if you fold, then phi 1 and phi 2 must match at the boundary, but their value is fluctuating. Mm-hmm. Yeah, so this is still correct in some sense. Yeah. And, so I will explain how to obtain this entropy correctly. Yeah. So the resolution is that okay. So you can take this basis. Yeah, of course. Choice of basis is your freedom. You can choose whatever basis you choose. But problem with this is that even though there is no explicit interaction in the Lagrangian which couples this field with those fields, they are not completely independent. That is because, again, considering this n equals to 2 case, so let's say this horizontal axis is phi 1, and the vertical axis is phi 2. Then, so phi 1 is compactified, means that you identify phi 1 with phi 1 plus 2 pi r, and phi 2 with phi 2 plus 2 pi r, means that this point, 0, 0, is identified with this point, 2 pi r. And this point is identified with this point, 2 pi r. So you can repeat. So this point is also identified with this point, this point. So these points are all equivalent, identified. So if I introduce a vector notation, phi 1, phi 2, vector, then phi is compactified like with a vector, and this vector belongs to some lattice. And so in picture, this lambda is nothing but this square lattice. So this is called a compactification lattice. And then, so now you can go back to this center of mass and difference field. So center of mass field is like choosing the axis in this direction. And this difference field is like your axis is running to. So you can choose this axis. It's a choice of basis. It's your freedom. But the point is that if you choose this new axis, then compactification of phi 0 and phi 1 are no longer independent. They are kind of intertwined. So the original basis, they are independently compactified. But in the new basis, this compactification is intertwined. So they are not completely independent in that sense. So in computing the boundary entropy, you need to take this into account. So multi-component, so there is as I said, even for single component free boson, there can be non-Dirichlet, non-Neumann boundary condition, but those are complicated, so I'm not going to discuss today. But if you go to multi-component free boson, then there is a natural generalization of Dirichlet and Neumann, which is, let's call it mixed boundary condition, which is kind of generalization. Meaning that, yeah, like this. So roughly speaking, you impose Dirichlet on some of the linear combinations and Neumann on the rest of the linear combinations. So this is example of this mixed boundary condition. But then this is, how to say, so this is characterized by Orthogonal n by n matrix. And so there's some current left moving current and right moving current. So I can impose some generalized condition such that this left mover current plus some right moving current applied to the boundary state should vanish. So this is a general condition. At least this is a sufficient condition for boundary to be conformal invariant. But so this, as a special case, you can choose this orthogonal matrix as a n by n identity matrix. Then you find the Dirichlet. And if you choose minus identity matrix, then you find a Neumann. But so if you have a single component case, then this R is just a one by one orthogonal matrix. So within this choice, in one component, single component case, these are the only choice. And you have a Dirichlet and Neumann. But if you have a multi-component, two components, three component, then this R becomes a 2 by 2, 3 by 3 matrix. Then there is more choice of orthogonal matrices. Yes.
This boundary condition is the condition to preserve the parallel, right?
Mm-hmm.
Isn't that slightly more restricted than conformal?
Yeah. So I'm saying this is a sufficient condition for the boundary state to have conformal invariance, not a necessary condition. So this is kind of, I'm imposing stronger condition. Okay. So yeah, then just maybe summarize this. So yeah, thank you for pointing out. So this is a sufficient condition for conformal invariance. So this is still a subset of more general conformal boundary condition, but still there is a degree of freedom of this orthogonal matrix of your choice for multi-component free boson field theory. So this gives you a conformal. Okay, so yeah, I'm a bit slow, but okay, so this maybe stop here for break.
Thank you very much. So now we resume the lecture.
Okay, so yeah, so now I want to switch the subjects to quantum computation, which sounds like completely unrelated to the first part, but there's kind of connection. So and I'm not expert at all on this subject, so don't ask me the question, or you can, but probably I cannot answer your question.
Sorry,
Anyway.
but you left open this rock. What is the end of the story?
Oh, so okay. Then maybe I should give you the correct answer. Maybe. So then okay. So this is a kind of generalized Dirichlet-Neumann kind of boundary condition in multi-component free boson, and so this problem can be regarded as special case of this R. So phi 1 equals to phi 2 equal phi n, and then center of so we wanted to deal with this kind of boundary condition. Then actually this is a special case of this generalization. So in this case, so this is Dirichlet for most of the linear combination, but it's Neumann only for center of mass field. So I can choose this one. So if I just have this identity matrix, it's completely Dirichlet. But I want to make this center of mass field to obey Neumann. So what I can do is to subtract some projector. So I choose this d vector as some vector in this diagonal direction, or element 1. Then, so this is not normalized. So if you want to normalize, you put 1 over square root n. So if I don't normalize, I need to put 1 over n. So this is also a matrix. So it's just -1 only for center of mass field, which means that you are imposing Neumann boundary condition for center of mass field. And rest of the linear combination obeying Dirichlet. So if you choose this orthogonal matrix and impose this condition, then you are solving this problem correctly. And you can construct a boundary state explicitly using this matrix, and then compute the ground state. Sorry, the Affleck-Ludwig boundary entropy, and the result is that somehow I call this P for some reason, and yeah. Oh yeah, so yeah, you're right. Thank you, thank you. Yeah, it should be 2 because you need to cancel this side. Yeah, thank you. Yeah, you're correct. Then so then what I get for the Affleck-Ludwig boundary entropy for this particular boundary condition can be obtained like this for general n. And if I put n equals to 2 case, so n equals to 2 case is equivalent to nothing, just a single component boson, then you artificially create the identity defect and fault the system at the center of system. Then if you put n equals to 2, 2 over 2, that's 1, and minus 2 over 2, that's 1, and minus 1 plus 1 is 0. So I get 1. And this is the expected result. So this is a correct result. And of course, if n is 3 or greater, then this is kind of not completely trivial boundary condition. So only for n equals to 2, you can map this boundary to this nothing in the bulk identity defect. So for n not equals to 2, this is still non-trivial Affleck-Ludwig entropy. But for special case n equals to 2, you recover this expected result. So this is a correct result, and I don't have time to go through all the calculation, but once you write down generalized boundary condition using this orthogonal matrix and use this orthogonal matrix, and then you can construct a boundary state explicitly and then calculate this guy.
You know the answer for the general R matrix?
I I don't have explicit formula, I guess, but if you give me orthogonal matrix, then probably I can compute. So yeah, now switch to quantum. So in quantum computation, you use qubits. So you have many qubits. So qubit takes two states, 0 and 1. And of course, you can consider any superposition linear combination of 0 and 1 for each qubit. And then you start from initial state. Initial. So often, initial state is chosen to be completely trivial state, like uh, 0, 0, 0, 0. And but as I will discuss later, so this may be simple choice of initial state, but in more general case, you can start from non-trivial state. But anyway, you need to start from some initial state, then apply quantum gates. That's basically apply unitary operator to. So you have the initial state, then each quantum gate is basically unitary operator acting on your state, and you may apply many quantum gates or unitary operators. And then even if you start from some simple state like this, by applying quantum gates, you create some more complicated state. And then in the final stage, do the measurement. And of course, in principle, you can measure any operator, including very complicated operators. But often you want to limit the discussion to simple operators. And let's say I limit the quantum measurement to measurement to so-called computational basis state. Basis. That's basically means that for each qubit, you can introduce Pauli operators. In condensed matter physics, you often write a sigma x, sigma y, sigma z. But somehow in quantum computation, people write x, y, z. So x, y, z is a Pauli operators. And this computational basis means eigenstate of this Pauli z. So measurement of only z operators. And then still, if you can apply any complicated unitary operator, then you can do everything you can do within this quantum computation scheme. But of course, in practice, what kind of quantum operation or quantum gates you can realize is not an easy problem. And also theoretically, often people want to limit the class of quantum gates you can apply in order to simplify the theoretical discussion. So there's a particular set of quantum gates called Clifford gates. That is generated just three kinds of operations. So one is called Adamar gate. Adamar gate is just an operation on single qubit. And so for single qubit, everything can be expressed as a 2x2 matrix. So the Adamar is just this 2x2 matrix. And another single qubit operation is S gate. So this is diagonal, but put some phase I to second component. And both are just a single qubit operation. So you know, only with single qubit operation, you of course cannot do much because you have many qubits and somehow you want to entangle different qubits and so on. And the third element of Clifford gate, okay, so one of the generators is finally the 2-qubit operation called C naught. So which is control naught, which means that if first qubit is 0, so this is a projection operator to 0 state in first qubit. Then if the first qubit is 0, then you don't do anything on the second qubit. So this does nothing. But if the first qubit is 1, then you flip the second qubit. And the flipping of the spin is realized by this Pauli X. So C naught gate for 2 qubit can be written like this. And the Clifford gates are all the possible gates generated by successive operations of these three types of gates. And of course, this is very, very limited set of quantum gates. And indeed, so these Clifford gates have very special property. That is often we consider Pauli strings. Is a product of Pauli operators on each qubit. So this is like a P1 acting on first qubit and P2 acting on second qubit. And you apply one of the Pauli operators to each qubit and take a product. And for each qubit, you choose identity which does nothing, or Pauli X, or Pauli Y, or Pauli Z. So you choose one of these Pauli matrix plus identity, then you apply this operator to each qubit. Then, so if you consider this set of operator and take product of two operators, because product of two Pauli operators are again Pauli operator. So this is basically forms a closed set under multiplication. But for example, xy is iz, so you get a phase factor complex I, imaginary number I. So to consider Pauli strings as a closed set under multiplication, I also need to introduce some phase factor here. This phase factor is plus minus 1 or plus minus I. So then this is closed under multiplication. Then specialty of this Clifford gate is that so if C is Clifford, so this if C is element of Clifford gate, that is some operation which can be generated by multiplication of these guys, then C and also P is this Pauli string. Then this transformation of Pauli string by this Clifford gate is also another Pauli string. So this is a special property of Clifford gates, which makes analysis simpler, but it, as I will discuss, this also means that Clifford gates by themselves don't have much computational power for the sake of quantum computation. And indeed, there is a famous theorem in this quantum computation business that is Gottesman. I forgot whether there is one N or two N, but Gottesman knew. Which says that if your initial state is the trivial in computational basis, like a 0000, and then only apply these Clifford gates, then do the measurement in this computational basis, or measure only Z, Pauli Z operators. So you can think of quantum computations which can be done within this setup. But okay, so I don't remember the proof, so I cannot explain, but their claim, this theorem says that this class of quantum computation can be efficiently emulated by classical computers. That means that there is no quantum speed up, no quantum supremacy within this class of setting. So yeah, this is very interesting, but kind of disappointing from quantum computation purpose, because people are talking about this quantum computation because they are supposed to be much faster than classical computers, but within this setup, you cannot gain speed up. Of course, this using Clifford gates is very restrictive. So you can introduce another element to generator, then things are very different. But suppose for some reason you only want to use Clifford gate. And suppose you still keep this measurement constraint. But still, you can change the initial state. So the next question is whether you can start from more non-trivial initial state. Then maybe you can gain quantum speed. And the answer is yes. So if you use some non-trivial states, then actually you cannot emulate entire process by classical computer. So at least in principle, you can have quantum advantage if you use appropriate initial state.
Are non-trivial initial states as easy to prepare as the trivial first?
Yeah, that's the issue I want to discuss. Yeah, but, so first we need to figure out in what sense non-trivial. That's the first question I ask. Yeah. Then next, I want to ask how to prepare such a state physically. So actually, yeah, since general answer is yes, which means that some quantum state has a kind of quantum resource. Quantum state. Resource for quantum computation. And maybe quantum computation people are better than us condensed matter physicists in naming things, making things fancy, because they somehow call this kind of resource for quantum computation as magic. So some states are magic, or some states have quantum magic. But then next question is then what kind of non-trivial state you need to do this? And naturally, we might expect that we need some entanglement in initial state because entanglement is source of many quantum, interesting quantum phenomena, and that's true. But it turns out that just having entanglement is not enough, as I will discuss shortly. Some quantum states might have a lot of entanglement, but they are not useful for this purpose. So we need another quantity to, characterize or quantify the usefulness or how much quantum resource or magic your state has. And to explain this, I need to introduce another notion, that is a stabilizer group. So stabilizer group is a subgroup of this Pauli group, or group formed by these Pauli strings. This is, but it has to be abelian, meaning commuting. Subgroup of Pauli. And, yeah, I didn't define Pauli group, but Pauli group is a group formed by those Pauli strings under multiplication. So let's say S. So then so S is part of this Pauli group. And then for any two elements of this stabilized group, S1 and S2 commute. So then each element of stabilized group is also element of Pauli group. So they are product of Pauli XYZ or identity. So you can choose these elements to have eigenvalues plus minus 1. So because it's product of Pauli groups, so you fix phase factor in some way, then eigenvalues are all plus minus 1. And then they all commute. So then so because they all commute, you can consider simultaneous eigenstate of all the elements of the stabilizer group, which has eigenvalue all plus 1 for any element of stabilizer group. So that is stabilizer state. This is for all element of stabilizer group. You apply this stabilizer element of stabilizer to this state, then you have plus 1 eigenvalue. So if your quantum state satisfies this property, then it's stabilizer state with respect to this stabilizer group. And yeah, so I wasn't quite familiar with this notion, but if you are familiar with models such as Kitaev toric code and so on, then you have star interaction, placket interaction, but they all commute. And quantum information people call this stabilizer Hamiltonian. That comes from this. So this Kitaev Hamiltonian, the interaction terms are elements of certain stabilizer group. Anyway, so if you can define stabilizer group and your state satisfies this, then it's a stabilizer state. Then I already explained that Clifford gate maps Pauli string to Pauli string. And in similar manner, if you have stabilizer group, then if C is Clifford gate, then this C maps this stabilizer group to some different group, but this is still another stabilizer group. So S is a stabilizer group. Then this is, so this is also, so this is generally different from original stabilizer group, but still stabilizer group. Meaning that, because I already explained, although not proved, that Pauli string is mapped to Pauli string. So, but stabilizer group is a commuting elements of commuting subgroup of Pauli group. But if two elements in this S commute, this transformation by Clifford gate also commutes. So this is also stabilizer. Then this has very interesting consequence. That is, so for example, this trivial state 0000. So this is a stabilizer state. For stabilizer group generated by just Pauli Z. So because for any Z, this is eigenstate with eigenvalue plus 1. So this is stabilizer state for stabilizer group. Very simple stabilizer group generated by Z. And now you apply Clifford gate. Then this C times 000. So this initial different state was completely trivial, but the Clifford gate is very limited set of operation, but still you can introduce entanglement and so whatever. So this resulting state can be very, very complicated. But because Clifford gate maps stabilizer group to another stabilizer group, so this state is still stabilizer state for new stabilizer group. For stabilizer group, which is a transformation of this very simple stabilizer group. And if you, I already erased, but if you recall the Gottesman-Quignou theorem, it says that if you start from a trivial state and apply as many Clifford gates as you like, and finally you do the Z basis measurement, but then it doesn't have quantum speed up. And now suppose I replace initial state by this guy, and this guy may look very complicated, highly entangled, but you can still prepare this state from this trivial state by Clifford gate. That means that if you use this as an initial state, this is still within the validity of Gottesman-Queneau theorem, meaning that you don't have any quantum speed. And I just showed one way, but what can be said is that as long as you use a stabilizer state for some stabilizer group as an initial state, then there is no quantum speed up. So no quantum speed up if initial state is stabilizer. Yeah, of course, this is when you only use Clifford gates. And of course, if you use more complicated gates, then it's fine. So, okay, so this was a question, but what kind of state we need to use is that having entanglement is, of course, necessary, but that's not the not sufficient. So what I need is that this state must be non-stabilizer. And then, of course, if you take any generic state, stabilizer state is still very special because you need to consider stabilizer group, abelian subgroup of some Pauli group, and stabilizer state is simultaneous eigenstate of all the element of the stabilizer group. So it's certainly very, very special. Yes. That's the next, yeah. So yeah, so the generic state may be not, is generally not stabilizer state. But from this discussion, we can see that in order to use initial state as a quantum resource for this kind of quantum computation, your state is better to be far from stabilizer state. So we want to quantify the degree of non-stabilizerness. So, yeah, that's exactly what you asked. So, how useful is your then to answer that, we need some measure of non-stabilizers. And okay, so again, I'm not expert, but the first measure proposed was exactly like how many non-Clifford gates you need to prepare this state. Okay, so which is well defined and reasonable, but to actually compute that quantity, you need to optimize the number of gates. So it's very, very hard to calculate. Then there was a different proposal, which has some shortcoming, I think, but still easier to calculate and can be related to other StatMech type concept. That is, yeah.
Are you sure that because to get something which is far away from being stabilized, that should be gotten advantage? So it's definitely
Hmm.
I mean, you have proven to us that if the stabilized state is no quantum then.
Yeah.
Now you want to quantify how far away you are from being that.
Right. Yeah. Yeah.
But that doesn't necessarily tell you that you will get quantum advantage.
That's yeah. So yeah, of course. You know, of course, you can. There are, the measure of non-stabilizerness is not unique. So there are several different measures, and how they are related to resourcefulness is a non-trivial question. Yeah, yeah, that's yeah interesting question, which I don't fully understand, but yeah, that's of course not trivial question. But first, I want to. So at least what I can say is that if your state has zero such quantity, then your state is stabilizer state, even though it looks very non-trivial. So first thing you can do is to evaluate such measure, and if this is zero, then it's stabilizer state, so it's not useful. But that's what I can say. And one of such measure, which is kind of useful, at least for us, is stabilizer Renyi entropy, which is so for given quantum state, so the definition is kind of simple. So this alpha is a Renyi parameter. As usual. And this sigma is m is a Pauli string. And this is your quantum state. So for, and you sum over all the possible Pauli strings, identity XYZ, for every combination. And for each Pauli string, I take expectation value, and then take power of 2 alpha, and then divide by 2 to the system size L, and then sum over take rho. So this is stabilizer Renyi entropy. And why we use this is that if your state is stabilizer state, then for stabilizer group, you get a plus one, basically. So that gives you zero. So this is normalized such a way that if your state is stabilizer state, then this gives you one. And so of course you have many Pauli strings which are not within stabilizer group, but for such Pauli strings outside the stabilizer group, the expectation value is zero, so that don't contribute. So you can easily see that if your state is stabilizer state, then this entropy is zero. So this mi alpha is zero if psi is stabilizer state. So if this entropy is non-zero, then it's not stabilizer state. So for computational purpose, bigger entropy is better. then yeah, in principle, you can give me your favorite state, and I can try to evaluate. But it's in general, I don't know how to do that. But another uh, question asked was how to prepare such a non-trivial state. And for condensed matter person like me, maybe one natural quantum state, non-trivial ground state, non-trivial quantum state is a ground state of some many-body Hamiltonian, which may be naturally real. Of course, you need to, introduce some coupling with heat bath, relaxation to ground state, blah, blah, blah. But at least the ground state of some many-body Hamiltonian is natural quantum state. Yes.
Just take a random product state that is not in the 0, 1 basis. It will have a humongous non-stable life.
Yeah.
You don't need to find them at all. Just take a product state that is not in the plus whatever, not in any eigen basis of product.
Um,
It's not have a humongous stable life.
that's all. Yeah, maybe you're right, but well, of course, if you consider hard random state, then probably it's very non-trivial. But you are saying random state for each in product.
Mm-hmm. It's not say not in the 0, 1,
Mm-hmm.
like state of the sigma 1 is
Okay. Mm-hmm. Then maybe no zero. Okay, I cannot see immediately, but maybe you're right. Maybe. Um, yeah, maybe. But let me discuss this ground state. So, how about yes? Yeah, I think because I thought, but it's probably this system size times log 2 or something. I thought exactly, but yeah. Of course, if each element is qubit, then yes. Of some anybody. And it doesn't have to be critical, but to relate to the first part, let's consider the, for example, ground states of 1D critical Ising. Of course, the transfer field Ising model. And in that case, in principle, we know what is a ground state, but of course, it's very complicated. But you can map this problem because this expectation value of Pauli string with expectation value of Pauli string with respect to your ground state can be written as some trace of this Pauli string times just a projection operator. Of course, this is a trivial um, kind of rewriting, but then so this is operator and this is operator, but we often I forgot the name, but we often map this operator to vector in Hilbert space of twice dimension. So this can be replaced by some vectorized version of the Pauli string. And inner product with vectorized version of this projection operator. So this is 2 to L dimensional. This ground state lives in 2 to L dimensional Hilbert space. But now I want to regard this operator as a vector in 4 to L dimensional doubled Hilbert space. Then this is inner product. And then this vectorized version of is like you just take a product of psi and its complex conjugate. So if your ground state is real, it's the same one. And in path integral, so you can imagine you have imaginary time, and you had some random state at imaginary time minus infinity. Then you do the time evolution, and then at time 0, you have ground state, because only ground state survives by the Hamiltonian time evolution. So you can consider two-dimensional field theory, and at this cut, you find the ground state. And doubled means that you need to consider the copy, two copies of the same field theory. So for each Ising model, let's say, I already have 2 copies of Ising model because of this. And then because you consider the replicas, so you further have replicas of the pairs. Yes. Hmm? Oh, so this is a complex conjugation of the wave function. Yeah, because it's a bra. Yeah. And so then the next question is how to deal with this vectorized version of the Pauli strings. And so, for example, sigma of 0 was identity. So this was 1, 0, 0, 1. And or this is sum of these projection operator. So if I vectorize this, then I, vectorize this. So this means that this is 0, 0 plus 1, 1. Because I just, de-interpret this bra as just another ket vector. So actually, this is like a Bell pair state. Well, one of the Bell pair state, if you look in this way, except for the normalization. So this is one of the Bell pair state. So you can also vectorize Pauli XYZ in a similar way. And they also give you other Bell states. Okay. So this is not my discovery. This my collaborator found this. So I contributed very little on this project, but my old papers on conformal field theory turned out to be useful for this discussion. Um, so in this way, so this inner product can be written as um, overlap with Bell states. So on right hand side, this psi and psi star are independent ground state of, let's say, critical Ising model. But on this side, um, you consider overlap with Bell pair state. So the Ising spin on one copy is stringly connected to the other copy. So yeah, you need some technical calculation, but basically what this gives you is that, for example, if you start from Ising model, then here you already have a doubled layer of Ising model. So this is Ising squared. Yes. Oh yeah. So this is given by the Z2 orbifold of C equals 1 free boson. But you need to introduce replicas. And what happens is that so you have 2 alpha copies or replicas of Z2 orbifold. And at tau equals 0 slice, you take an inner product with this Bell state, which couples everything. So this basically imposes coupling. So from field theory point of view, well, you need to sum over M and so on, but the bottom line is that in order to calculate stabilizer linear entropy, we want to compute this kind of overlap. And in field theory, this is mapped to boundary problem because this ground state is result of the time evolution. And then inner product with this Bell pair state introduces a coupling. So actually, this is very similar to the problem I discussed in the first part. And the difference is that you need to take care of this orbifold business, but otherwise, yeah, it's very similar. So again, the center of mass field remains free, but the relative coordinates are fixed by interaction induced by this Bell pair coupling. So at the end of the day, this stabilizer linear entropy for this Ising chain ground state is related to the boundary free energy of this 2 alpha replica couples at the boundary. Then,
I think that system is exactly conformal.
well, yeah, of course, not exactly conformal, but the hope is that um, the boundary condition induced by this kind of operation is microscopic. So by itself, it's not conformal. But if you consider the large scale behavior, any boundary condition is renormalized into one of the conformal boundary conditions. So yeah. So the continuum limit or you know low energy limit or something like that. Sort of, yeah. Uh, so then this SRE from this field theory statmech point of view is given by sum of two parts. So one is the boundary free energy, which is non-universal. And another part is the universal Affleck-Ludwig, which we can calculate from conformal field theory by using a similar trick as I discussed in the first part. Yes. Yeah, so we try to interpret this Bell state. Yeah, so of course not rigorous, but we can argue that we need to introduce certain boundary coupling to reproduce this kind of state. Some hand waving RG argument. But by assuming certain boundary state, like I discussed in the past part, we can calculate this and compare with the numerical calculation, which seems to match. But as far as quantum resources are concerned, actually this is a small part compared to this non-universal part, which is proportional to the length. So maybe for practical purpose, so this quantity is theoretically very interesting, universal, blah, blah, blah. But as a resource, actually this term is more dominant. But on the other hand, yeah, we can say that this non-universal part is not restricted by conformal field theory. So by choosing some model, you can increase this. But anyway, theoretically, appearance of this Affleck-Ludwig universal boundary entropy in this stabilizer linear entropy is kind of interesting because this is, at a first glance, it's not, doesn't seem to be related to this kind of problem, but it is, yeah.
I think you want to check whether the result is not zero, so you only need to see whether G is different from 1, so you don't need that from 0.
But you need to kind of fit with both terms. So
Yeah, but this A different can be there, so you expect G is different from 0, the result is different from 0. So if G is different from 1,
mm-hmm.
then the result will be different from 0.
Sorry, I still don't get.
Comparing 0 with this quantity, how would you compare?
how.
You said that if it is not useful ground state.
Well, but again,
Now
you have combination of these two. So
but the bad state was just zero full stop.
um, but so I forgot the exact formula. But this also depends on Lenny parameter alpha. But anyway, so um, what to say? So the actual resource is sum of this non-universal term, which is proportional to length plus this constant term. So even if this happens to be zero, you can have resource. But this is non-universal, meaning that it depends on microscopic model. And sorry for running over time, but that's what I think.
Is there a variant of this last Blackboard, not on cosmology theory, but topological theory, where you don't have the first term, and you can also use it as a topological computation?
Yeah, good question. Yeah, I want to actually explore that kind of question, but I don't know. From lattice point of view, you probably always have this because you are introducing some boundary different from bulk. Then there is usually boundary free energy, which is proportional to the length of the boundary or area of the boundary.
Not critical. If it's a gap theory, it's not critical. You don't have.
No, even in gap theory, I think you have so for gap theory maybe you don't have this one, but my understanding is you always have this, except for some very fine tuned case. That's well, maybe I'm wrong, but that's my understanding.
Sasha is looking at me really. It's really fast.
I'm just still missing the connection. It was asked already, but we know that if Brennan, you showed that if Brennan entropy is zero, then yes, this cannot be used as one resource. But who says that if you have it non-zero, you still can use it as one resource, or even if that it's a measure of how useful the state is?
Yeah, there are some papers which sorry I haven't really digested. But yeah, one thing is that what was the theory? I forgot. But so in StatMech, people are often interested in Feynman entropy, which is alpha goes to one limit of this Renyi entropy. So Renyi entropy is kind of trick, replica trick, just a step to obtain Neumann entropy. But for quantum computation purpose, I forgot details, but let's say alpha equals to 2, Renyi entropy has certain meaning. It gives some certain useful bound for this computational resource or something. Yeah. So there are many discussions how to characterize resourcefulness using this, and it does depend on many parameters. So it's interesting field, but I don't fully, I'm not fully following this business.